Welcome everyone, I'm Norman Wahlberger. Today we're continuing on talking about our 10th famous math problem, which is the integral of x to the n. More specifically, we're trying to define and establish this particular formula, usually called Cavalieri's formula, which is that the integral from 0 to a of x to the n dx is equal to a to the n plus 1 over n plus 1. For n, a natural number, or 0. So 0, 1, 2, 3, 4, and so on. We saw that the easiest cases, n equals 0, 1, and 2, were essentially solved in antiquity. And Cavalieri in the 17th century, along with other mathematicians at that time, dealt with the cases n equals 3 to 9 and beyond. So part of the problem with this issue is that we need to first of all define what the integral means before we can establish it. And in today's lecture I want to introduce a new simplified way of thinking about what the integral means. And then I'm going to give you a remarkable and elegant new derivation of Cavalieri's formula. So this is something that's new, that you can't see in calculus text, and I'm going to show you a derivation which is really quite magical and opens the door to what we might call the algebraic calculus, which is a new way of thinking about a very important subject of calculus. Our first approach to the integral is the standard one that's usually found in most first year, second year, third year undergraduates' texts. It's called the Riemann integral. Although probably the 17th century mathematicians would wonder why a 19th century mathematician gets his name associated to this, because it's really essentially the same kind of idea that was well known in the 17th century. Okay, so we have some function f of x. Let's picture it like that. We have some interval a to b. What do we mean by the integral of a to b f of x dx? Well, what we do is we look at a partition of a to b. That is, we divide up this interval a to b into a certain number of subintervals and call that division the partition p. And then on top of that partition we create a bunch of rectangles. We make the largest rectangles that we can that lie completely underneath the graph of the function. Okay, that's these green rectangles here. And then the sum of these areas is some kind of approximation to the area under the graph. But it falls short of the area because it's obviously going to be less than the area of the function, at least if the function is positive like we're showing it here. To complement that, we also look at another construction of rectangles using the same partition P. Here's supposed to be the same function f of x. And now over every little subinterval we create a rectangle which is totally above the function. So the smallest rectangle that's totally above the function over that interval. So that rectangle there, that red one, then that one there, that rectangle there, and so on. So these rectangles here are encasing or enclosing the region, while these ones are sort of inside, sort of inscribed rectangles and maybe circumscribed rectangles. So this kind of idea of thinking about something filling in a region from the inside and then another sum filling the region from the outside goes back to Archimedes' calculation of pi with regard to the area of the circle. So it's a very classical idea of trying to bracket what we want between a lower bound and an upper bound. All right, and then the idea is to take these two numbers, these areas of the green rectangles and the red rectangles, and then take a limit as the partition P, its norm approaches 0. So as the partition becomes finer and finer, we look to see whether there's a limiting common value between the lower bound and the upper bound. And if there is, then we call that limiting value the integral from a to b of f of x dx. All right, there's all kinds of technical issues here. There's issues about what happens when the function is dipping below the x-axis, what happens when there's continuity, and then there's a whole bunch of theorems that one has to prove about when this integral is defined and what properties it has. Okay, so there's a lot of work to be done even once we have the basic idea in our minds. So this is a standard integral that most undergraduates will be familiar with, at least informally, in terms of some kind of intuitive picture. But the Riemann integral is by no means the only possible approach to defining an integral using the idea of areas. There's a somewhat more sophisticated version of the integral due to a 19th century mathematician, Lebesgue, where one essentially slices the region not with a lot of rectangles going up and down, but rather with slices going across, left to right. As I've indicated here, so we kind of imagine partitioning this region, the y-axis, into subintervals, and then using those to slice the region in question into bands. And then the idea is to use the areas of these bands as some kind of approximation to the integral. So roughly speaking, it's an approach like the Riemann integral where we sort of look at horizontal slices rather than vertical slices. And it has quite a different character. Another possible approach is to take our function and superimpose on the plane a grid, like a piece of graph paper. Lots of little squares covering the plane, and then what we do is we look at which of those squares lie inside the region that we're thinking about. So for example here, the green squares would lie completely inside the region under the graph. And then we might also consider those squares which cover the region at least partially, which would then include these red squares as well. And then the idea is that the area of the green squares added up and the area of the green and red squares added up is some kind of lower and upper bound to the actual area, whatever that is. So we could get at the area by using a grid of size, say, 1 over n, and counting grid squares inside and out, and then letting this number n approach infinity or get large. In other words, we use a finer and finer grid paper to make our approximation more and more accurate. So that's another approach to the integral. We might call that the grid integral. Yet another approach we might call a piecewise linear integral. And there the idea is that we would take our function f of x and replace it with a piecewise linear approximation. So you could do that by sampling the function at some reasonably equally spaced points, and then just connecting those adjacent points with straight lines. So you get a simpler version of the function, an approximation to the function, and then the idea is that the area under that linear or piecewise linear function is going to be relatively easy to calculate, just a bunch of trapezoids, and then that area is an approximation to the area underneath the function, and the closer these points here are spaced together, the better the approximation will be. So again, it's another limiting procedure where the piecewise linear approximation becomes better and better by choosing more and more points. Another possible approach to the integral is to think about a polygon, to think about the graph and the two sides and the x-axis as forming some kind of, well, something that's almost a polygon. So by choosing randomly spaced or arbitrarily spaced points on the function, we could create a polygonal approximation to this region with just a finite number of sort of vertices. And then we could calculate the area of that in the sort of standard way, say by triangulating it. We could choose some point and then divide this polygon into a whole bunch of triangles, and then perhaps we could use the formula for linear algebra in terms of a determinant to calculate areas. So those are some possible different ways that one might try to set up a theory of area. All of them rely on some kind of infinite processes. Now, whichever approach you take towards trying to set up an integration theory, you are going to want to establish certain basic properties of your integral. And I want to list some fundamental basic properties that are going to be crucial in any theory of integration. The first we might call the linearity properties, and there are two of them. And the first one says that if you integrate f of x plus g of x, so the sum of two functions from a to b, that should be the same as the integral of f of x from a to b plus the integral of g of x from a to b. And going along with that, this one here, that if you integrate k times f of x, where k is some number, then that should be k times the integral of f of x. So this sort of corresponds to an additivity in the y direction. This one here, for example, corresponds to what happens if you scale the picture by multiplying f of x by a factor k. It means you're scaling everything by a factor k in the y direction. And so it's natural that the area will then be multiplied by k, no matter what definition of area you end up choosing. The second property we'll call additivity, and that will be that the integral from a to b of f of x dx plus the integral from b to c of f of x dx should equal the integral from a to c of f of x dx. That's only natural, right? Here's an interval a to b, and then another interval b to c. Well, the area under here plus the area under here should be the area under the big interval a to c. Now, once we have this particular property, it makes it clear that the particular integrals from 0 to a play a somewhat distinguished role, in the sense that if we have the integral from 0 to a plus the integral from a to b, then we're going to get the integral from 0 to b, which means that the integral from a to b can be thought of as the difference between the integral from 0 to b and the integral from 0 to a. In other words, if you know the integrals then from 0 to some arbitrary number a, then you know all the other integrals by taking appropriate differences. A third very important property that you'll want to establish is that your integral is translation invariant. In other words, that if you move the function by translating it a certain amount, and move the interval that you're integrating with accordingly, then the integral is not going to change. So the integral from a to b of f of x plus c dx is the same as the integral from a plus c to b plus c of f of x dx. You can kind of see that here, when x happens to be a, then we're evaluating f at a plus c. And at this endpoint, when x is b, we're evaluating f at b plus c. So it makes perfect sense that this is the same as the integral of f of x as x goes from a plus c to b plus c. Just a translational property of the integral, or the area. The fourth property is a little bit like the translation invariance. It's describing what happens when we scale along the x direction. We've already talked about what happens when we scale along the y direction. If we scale by a factor of k, then the area, or the integral, gets multiplied by k. Well, the same kind of thing should happen if we scale along the x direction. And here's the corresponding statement in terms of the integral. It's a little bit more complicated, so I've illustrated it with an example. So the formula is that if we have the integral from a to b of f of c times x dx, and we multiply that integral by c, then we get the integral from ac to bc of f of x dx. All right, so that's a little bit of a complicated formula. Let's try to understand it in terms of this example. So I have two intervals here. I have the interval from 1 to 2 and another interval from 3 to 6. And let's say that this is the function f of x. So the right-hand side, we're talking about the integral from 3 to 6 of f of x dx. It's exactly the area under this function f of x from 3 to 6. All right, now let's think about this function f of 3x. So here is the function f of 3x from 1 to 2. It's obtained from this function by scaling, essentially by scaling by a factor of 1/3 in the x direction. So let's see how we can see that. The function f of 3x at the point x equals 1, well, that's f of 3. So that value is going to be the same as the value of f at 3. On the other hand, the value of this function at 2 is f of 3 times 2, or f of 6. That's going to be the same value as function f of x has at 6. So the effect of putting this 3 in here is that we're scaling all the values over by a factor of 1/3. And that scaling means that this integral is 1/3 this integral. So to make equality out of things, we have to multiply this integral by 3 to compensate. All right, so 3 times the integral from 1 to 2 of f of 3x equals the integral from 3 to 6 of f of x. That's a particular case of this scale invariance property. And the final property, perhaps the simplest one, is a normalization property. That if we look at the integral from 0 to 1 of the simplest function 1 dx, we should get 1, because that represents the area of a box of base 1 and height 1. So these are 5 important properties that any integration theory will want to establish. So no matter which direction of an integral you define, whether you choose a Riemann type integral or a Lebesgue type integral, or maybe some kind of partitioning or linear piecewise integral, whatever definition you choose, you will want at some point to establish these 5 properties of your integral. Because these are the properties that are analogous to the familiar properties of area when we translate areas or we scale them in the usual way. All right, so now we come to the main theorem. Here is our million-dollar derivation. We are going to evaluate now the integral from 0 to a of x to the n dx. And I'm going to do this in a way that does not depend on which choice of integration theory you give me. So the scenario is something like this, that you have developed an integration theory. It can be one of the ones I've described. It can be maybe some other one. And you come to me and say, Norman, here's my integration theory. I can explain it all to you. And I want you to evaluate this thing for me. How do I actually compute what this is in the context of my integration theory? Well, I'm going to tell you I can do that for you. And you'll say, well, okay, so now I'm going to tell you about my integration theory. And I can say, no, I actually don't want to know about your integration theory. I only am concerned with whether you have already established the 5 properties that I've described. Linearity, additivity, translation invariance, scale invariance, and normalization. Have you established those properties for your integral? And you say, yes, it was quite a lot of work, but I have done that. And I say, great, that's all I need to know. I am now going to compute this integral for you, independent of what your particular integration theory is. How am I going to do that? I'm only going to use those 5 properties. So I'm going to circumvent any infinite processes that you have used in your definition of the integral. Okay, it takes some while to get the idea here, but the idea is actually very simple, and you're going to see that the calculation is remarkably elegant and simple. You'll all be able to follow it. It's only 2 slides long. All right, so the theorem is, somewhat informally, that if your definition of the integral from a to b of f of x dx satisfies the 5 conditions that I have listed, conditions 1 to 5 above, for polynomials, then the integral from 0 to a of x to the n dx is indeed a to the n plus 1 over n plus 1 for n equals 0, 1, 2, 3, 4, and so on. In other words, Cavalieri's formula applies. All right, so we're now going to prove this. And you will probably want to write this proof down and study it and think about it. Okay, it's short and sweet. The first thing we're going to do is we're going to define a special case of this thing, the special case when a equals 1. So the integral from 0 to 1 of x to the n dx, we're going to call that a sub n. That's some number. And there's such a number for n equals 0, for n equals 1, for n equals 2, for any higher natural number. All right, what do we know? The first thing that we can say is that by condition number 5, our normalization condition, a sub 0 is actually equal to 1. Because when n is 0, then x to the 0 is the function 1. We're talking about the integral from 0 to 1 of 1 dx, and we have agreed that that is actually equal to 1. So we know what a sub 0 is. All right, another important property, the scale invariance, implies the following. Suppose we look at the integral from 0 to 1 of a times x to the n dx and multiplied by a. According to the scale invariance formula, this is equal to the integral from 0 to a of x to the n dx. So this is a special case when the interval here, which used to be called ab, is 0, 1. This number a is playing the role of c in the formula. And the function that we're talking about is the function x to the n. All right, so please make sure that you see that this is the scale invariance property. For first-year students of calculus, it's also just integration by substitution. We can just substitute to go from here to here. All right, well, this thing here, the integral from 0 to a of x to the n dx, well, that's really what we're interested in, isn't it? That's what we would like to evaluate. So let's look at this. What we know from here is that this number, whatever it is from this left-hand side. We can bring this a to the n out front. We can do that by property 1, the linearity property. So if we bring that out front, we get a to the n plus 1. And what we're left with here is the integral from 0 to 1 of x to the n, which we've agreed is a sub n. So the quantity that we're interested in, the integral from 0 to a of x to the n dx, is a to the n plus 1 times a sub n. So we've established that by using property 4 and property 1. And now comparing that to what we want, we see that we'll be finished if we can prove that a sub n equals 1 over n plus 1. If we can do that, then we will have established Cavalieri's formula. So we want to prove that capital A sub n actually is 1 over n plus 1. All right, what we're going to do now is we're going to look at the integral from 1 to 1 plus c x to the n dx. what do we know about this? Well, using the additivity property, we can write that as the integral from 0 to 1 plus c of x to the n dx minus the integral from 0 to 1 of x to the n dx. The advantage in doing that is the integral from 0 to 1 plus c of x to the n dx is, according to the formula that we've just established, 1 plus c to the n plus 1 times a sub n. Remember, we've just established that the integral from 0 to, say, a of x to the n dx is a to the n plus 1 times capital A sub n. So the a is being replaced with 1 plus c here. So we get 1 plus c to the n plus 1 times capital A sub n. And then we have to subtract the integral from 0 to 1, which is by the same thing, 1 to the n plus 1, which is just 1, times a sub n. So we're using the previous formula that we've established together with property 2 additivity. Okay, now this is the binomial theorem here. We have 1 plus c. We need to raise this to the n plus first power. And that's exactly the binomial theorem. And so here's the binomial expansion of 1 plus c to the n plus 1, where I've lopped off the first term because it gets removed because we have to subtract 1. So the first term, which would otherwise be 1, is removed, and then the next term is n plus 1 times c, and then n plus 1 choose 2, c squared, and then n plus 1 choose 3, c cubed, and so on, all the way up to n plus 1 c to the n, and the last term just c to the n plus 1 by itself. That's the expansion of the binomial theorem of just that. And we still have to multiply everything by a sub n. It will turn out that in this formula, this first term is all what we really need. Okay, so the other terms, in fact, don't really figure prominently. Okay, now we're going to take this expression and we're going to rewrite it using the translation invariance property, property number 3. The integral from 1 to 1 plus c of x to the n dx is the same as the integral from 0 to c of 1 plus x to the n dx. Right, when x is 0, we get 1 here, and when x is c, we get 1 plus c, so it's exactly the same thing. Now we're going to expand what's inside the bracket using, again, the binomial theorem, except now it's 1 plus x to the n, which is 1 plus n times x plus n choose 2x squared plus n choose 3x cubed, and so on, all the way up to n times x to the n minus 1 plus x to the n all by itself. So all of those things dx. All right, and now we're going to use linearity. The fact that the integral of f of x plus g of x is the same thing as the integral of f of x plus the integral of g of x. Well, but we're going to apply it a number of times, so we're going to have one integral term for each one of these individual terms. So we get the integral of 1 dx, the integral of n times x dx, the integral of n choose 2 x squared dx, and so on all the way up to the integral of x to the n dx. And I've also used linearity once more to pull out this n from inside to the outside, to pull out the n choose 2 from the inside to the outside, to pull this n from the inside to the outside. Can we evaluate these kinds of integrals? Yes, we can. Again, that's the basic property that we've already established. So this thing here is the integral from 0 to c of 1 dx. According to our formula, that's c times a sub 0. This is actually x to the 0. So we're going to get c to the 0 plus 1 times a sub 0. This next one is an n. The integral from 0 to c of x dx, using that basic formula we established, we get c squared times a sub 1. The 1 because this is x to the first power. And then n choose 2 times c cubed times a sub 2. All the way up to n times c to the n times a sub n minus 1 plus c to the n plus 1 times a sub n. All right, all of these things are equal. In fact, the only thing that we need in here is actually the first term. So these other terms are actually incidental. Just as up here, all these terms are incidental. The only thing that we really need out of all of this is to look at the first term of this expression and the first term of this expression. So let's have a look at this. First of all, this is a polynomial in C. Okay, n is fixed. This is a polynomial in this unknown number C, which is variable. So this polynomial in C equals this polynomial in C. So these two expressions are equal for many values of C, for more than n values of C. These polynomials have to be equal then. If two polynomials agree on, well, more than n terms, then they have to actually be equal. And that means that the linear term here and the linear term here have to be equal. So n plus 1 c times a sub n has to equal c times a sub 0. But remember, a sub 0 was 1. And that's telling us that n plus 1 times a sub n is equal to 1, so that a sub n equals 1 over n plus 1. That's exactly what we wanted to prove. So that formula that we had on the previous page tells us the integral from 0 to a of x to the n dx is a to the n plus 1 times this a sub n, which is 1 over n plus 1, and that is Cavalieri's formula. So we have established Cavalieri's formula for a general n, natural number n. We're using the binomial theorem here for natural numbers. We've done it without any infinite processes. We've done it without any sophisticated concept of the integral. All what we've really used is the 5 properties that the integral should satisfy if it's going to act like an area. So even if you had now a very physical, intuitive, no-nonsense approach and said, look, Norman, let's just pretend this is an area. What's the integral of x cubed dx from 0 to a? Well, I would just argue we're just talking about basic properties of areas. These are 5 basic properties of areas. The integral has to be a to the 4th over 4. It's a high school calculation without any infinite processes, without any use of real numbers. We only use the rational numbers. The workhorse is really the binomial theorem. All right? The binomial theorem is really the crux of the matter. It's perhaps a bit of an exaggeration, but not much of an exaggeration, to say that calculus is an application of the binomial theorem. There's some truth in that. All right, this argument would be accessible to Cavalieri. If we went back to Cavalieri's time and I showed it to him, he would probably go, yes, of course, why didn't I think of that? It's not so different from the kinds of manipulations and thinking that he was doing. All right, so there are many interesting consequences to this derivation. First of all, it allows a definition of the integral on polynomials in terms of basic properties 1 to 5. So we can now sort of reverse the argument and say, look, we're going to define the integral not in terms of any infinite processes, but in terms of the properties 1 to 5. In other words, we can establish what the integral is in terms of the properties 1 to 5. And this can be done in a number of ways. For example, one can set it up in terms of a linear transformation from polynomials to polynomials that satisfies certain basic properties 1 to 5. I've already mentioned it really only requires high school arithmetic. The rational numbers are what's necessary. No infinite processes or limits are needed. All right, this is an insight that should give pause to anyone who teaches calculus. Okay? It's showing that there is an alternate way of thinking about things, a simpler way, more elegant, more algebraic way. Okay, it also extends to general fields because everything's just algebraic. So, for example, the argument can be extended to complex rational numbers. And when we do that, we're basically capturing the essence of so-called complex line integrals. Okay, so in complex analysis you also have to define integrals, but you have to define them in terms of line integrals, and it's somehow analogous to area, but it's not really like area anymore. But it turns out that the line integrals that you define are basically satisfying the same properties that I've described, 1 to 5, on polynomials. So an integral formula like this will be almost immediate. The integral of z to the n dz over some gamma is going to be a to the n plus 1 over n plus 1 for natural numbers n. And because everything's algebraic, well, it allows us the idea of, well, maybe we should be thinking about integration over finite fields. So there are finite fields, like prime fields. The argument essentially works. What does it mean? What is an integral over a finite field? It's not so obvious what area means anymore. It's certainly clear that infinite processes don't exist, so an approach to integration via infinite processes is not going to work very well for finite fields, probably. But we see that algebraically this integration theory does work. Although we have to be a little bit careful. With finite fields, say a prime field, we have to worry a little bit about what might happen if this denominator is 0. So if we're working over a prime p, then if n is equal to p minus 1, then there's going to be a 1 over p here, and that's like 0. Right? So there's going to be some exceptions that occur in the finite field that don't occur over the rational numbers. In any case, it's an interesting challenge to think about what does it mean to do calculus over finite fields. I think that's going to be an interesting sort of direction for calculus in the next century or so. So some of you can start thinking about that. So the main reference for what I've presented today is in this very short paper of mine called A New Proof of Cavalieri's Quadrature Formula, which appeared in the American Mathematical Monthly in 2002. It's only a couple of pages long. The argument there is pretty close to the one that I've given you today, but I think actually the one that I give you today is a little bit better. One of the advantages in doing this kind of YouTube adventure is that I get to rethink things and have a look at them from some novel point of view many years afterwards. And so I think in this case my argument here is just a little bit preferable to the one that I gave here, but it's more or less the same kind of story. Obviously there's a lot of details here and new directions that require more thinking and more work. I'm going to talk more about this topic and the algebraic calculus more generally in my Math Foundation series. All right, so I will be revisiting this, but this calculation that I've presented to you today is going to be a crucial calculation that sets up this possibility of doing integration algebraically. Okay, so in our next famous math problem, we're going to go back to a very famous geometer, Jacob Steiner, and a problem that he posed having to do with three-dimensional space. He asked the question, suppose you take a plane in three-dimensional space. Well, it divides the plane into two regions. And then if you take two planes which cut each other, they divide space into four regions, at least if the planes are not parallel. And he asked the question, what's the maximum number of regions that you can divide space into with n planes? It's a lovely problem. We're going to give the solution. You might want to think about that before then. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.